Hi everybody, Dr. Ahles here. In this short video, we're going to remind ourselves the difference between an autosome and a sex chromosome. And we're going to talk about some of the genetic disorders that are passed along on the X chromosome. Remember that in the human genome, we have 22 pairs of autosomes. And these are the types of chromosomes that code for all of your non-sex related functions. So your hair color, your eye color, your height, all of that kind of information is stored in these autosomes. We also have one set of sex chromosomes, and there are two options for sex chromosomes: the X, as we see over here on the left, or the Y, that's much smaller, that we see here on the right. When we talk about the X and Y chromosome, there's one gene in particular that's very important for determining an offspring's sex. And this is a gene called the SRY gene. The SRY gene is responsible for helping a developing embryo to start creating testosterone. So in a female embryo that only has two X chromosomes, this gene wouldn't be present. Testosterone would not be made. But in a male embryo with an X and a Y, this gene becomes activated, leads to the synthesis of testosterone, which ultimately helps with the development of the male gonads, the testes. So up to this point in development, which is maybe around week 8, male and female embryos will look the same until we activate this SRY gene to cause that differentiation. When we think of the X and Y chromosome, primarily we think of them as the sex chromosomes, but there are a lot of other genes on them, as you can see from our pictures here. I will not ask you the names of these genes or what they do, but I just want to make you aware that there are lots there. One random example of a gene that we find on the X chromosome is something called the CT genes. And these genes are something that your body actually specifically scans for when they look for the name tag of cancer cells. So when a cell is cancerous, it's expressing these genes, creating markers that we can use to determine if it's cancerous or normal. When we talk about the process of reproduction, remember that males and females both contribute half of their genetic information to their offspring. So females have 2 copies of the X chromosome, while males have 1 copy of the X chromosome and 1 copy of the Y chromosome. When a male creates their gametes, there are 2 possibilities for what sex chromosome they're going to pass along. Either they'll pass along their X chromosome, or they'll pass along their Y. When we talk about a female making gametes, every time she will always pass along an X chromosome. This is what she has 2 of. When she splits it in half, it goes 50-50 either way. But because she has 2 of them, it's important for you to realize that even though they're both X chromosomes, they might have slightly different versions or different alleles of genes on them. So in our picture here, we're looking at 4 different offspring that could potentially be created by this parent group. In some of the offspring, mom gave her green circle, X chromosome. In some of the offspring, mom gave her white circle, X chromosome. Some of the offspring, dad gave an X. Some of the offspring, dad gave a Y. Remember, when we're talking about sex determination, it all comes down to the male gametes. Is the male giving an X? That would lead to the development of a daughter. Is the male giving a Y? That would lead to the development of a son. Because mom always gives an X chromosome, whether it's her first X or her second X. That's the only kind of sex chromosome she can pass along. Because females have 2 X chromosomes, they have to go through and actually inactivate one of them. Each cell only needs 1 X chromosome to be functional. So early in embryonic development, each of the cells in a female's body will go through this random process of deactivation. What happens with the X chromosome that got deactivated is we turn it into something called a bar body. And I want you to underline, highlight, star that word, bar body. This is what I call the X chromosome That's deactivated, it's been collapsed down. The genetic information that's stored on that X is inaccessible to the cell. It's only going to use the other X to get that information. When we look at the group of cells early in embryonic development, it's important to note that not every cell turns off the same X chromosome. So in my picture that I see over here, I have an orange X and a black X. If you look through each of these cells in this developing embryo, some of them turned off their black X, some of them turned off their orange X. So we can see a little bit of mosaicism. So think of a mosaic with lots of little pieces. We can deactivate different X chromosomes, leading to that mosaicism, or that differences in bar bodies. This actually plays out very vividly when we look at what are called tortoiseshell cats, or sometimes they're called calico cats. In these types of cats, why we see these different colors in their coat is because the gene for coat color in these types of cats is found on the X chromosome. During early embryonic development, different X chromosomes are turned off in the cat. So some of the X chromosomes that are turned off are for the black gene. Some of the X chromosomes that are turned off are for the orange gene. So we end up with a cat that has a very different pattern throughout its coat. And the reason it has those differences is because some of the orange genes or some of the black genes got turned off, leading to the appearance that we see at these different locations. Now keep in mind, we will only ever make a bar body in female offspring. Remember that male offspring only have one X chromosome. We will not turn off their one X chromosome. So X inactivation only happens in females because females have two X chromosomes. We also briefly touched on this, but I want to go a little bit more in depth to the process of what are called X-linked genetic disorders or sex-linked disorders. It is possible for genes leading to a genetic disease to be present on the sex chromosomes. Often we're talking about on the X chromosome because it's much larger. There are a few that are located on the Y chromosome as well. When we look at what we call a sex-linked or X-linked dominant disorder, you will notice that males and females are both regularly affected by this disorder. So in a dominant disorder, remember that you only need one copy of the disease allele to express the phenotype. When I look at this father, he is expressing the disorder. His phenotype says he has a copy of this allele, but it's on the X chromosome, so dad only gives that X chromosome to each of his daughters. Each of his daughters express that phenotype. Each of his sons get their X chromosome from mom. Mom doesn't express it. But say that this son reproduces with a woman who also has the disorder. When she passes along her information, she's going to give it to both her sons and her daughters, some mix of them, because she has two copies of this trait. The biggest way to figure out that we're looking at a sex-linked dominant disorder, find a male who's affected. If all of that male's children, all of their female offspring, are expressing the disorder, that's X-linked dominant. We can also have X-linked recessive as well, though. And when we have an X-linked recessive disorder, you're going to more commonly see this being expressed in males. This is because, recall, males have one X chromosome. So if I'm a male and I have my one X chromosome with the allele for this disorder, I'm going to express it. So notice when I have a male in this pedigree that comes from a female expressing the disorder, both of those male children are affected. Again, I have another female who has this disorder. Both of her male children are affected. When we look over here, we've got a mom and a dad. Neither of them are exhibiting the disorder, but they have a son who does have it. When we talk about a recessive disorder, remember that in recessive disorders, you can have carriers, people who have the allele, but they also have a dominant trait that silences that recessive allele. So in a sex-linked recessive disorder, the easiest way for you to know for sure that this is a possibility, when you have a female who is affected, that means she has 2 copies of the recessive allele. All of her sons will express that phenotype because they're definitely going to get a copy of the allele for that disorder. So remember, when we looked at pedigrees previously, we talked about this idea of people being carriers. In this particular pedigree that we're looking at, they represented carriers with a black dot in the middle. So we're still looking at an X-linked disorder. I'll tell you the way I can tell that is because the only people who are carriers are women. So carriers have 2 copies of the allele. They have a good copy and a bad copy. If only women have a bad copy of the allele, it must be on the X chromosome. And as we look at each generation from the original parents to their offspring, notice that the only offspring actually affected by this disorder is a male. We go into the next generation. Neither mom or dad is expressing the disorder, but notice that both of their boys are expressing it. Again, we go into the next generation, and the only kind of offspring expressing it are males and males. This is a great example for us of an X-linked recessive family tree. But again, remember, the other way we could tell, even if we didn't check out how all the males are the ones who are affected, the other way we can tell that this is an X-linked recessive trait is because we have those carriers. Remember, anytime you have a carrier, whether it's for a sex-linked trait or whether it's for a trait on an autosome, it always has to be recessive. If I can carry it and not have the disease, I must need 2 copies to express that disease. So as you're reviewing pedigrees, both from this chapter with the sex-linked traits and from the previous chapter with our autosomal traits, practice looking at pedigrees to figure out what kind of transmission we're seeing. Is it dominant? Is it recessive? Is it an autosome? Or is it, as we talked about today, a sex chromosomal disorder?